the inverse trig functions. That's what we were doing last time. I actually thought, I probably should have done this last time, but I thought maybe it would be nice to do a little just kind of lightning review of trigonometry. Would that be helpful to anybody? Sines and cosines and such? So, I'm going to tell you what I expect you to know about sines and cosines. Like, there's a lot of, there's kind of a lot of stuff, and you know, it was all part of your course last semester, I hope. That's right. That's correct, right?
Yeah.
We covered this sines and cosines. All right. So here's a little trig review. Come on now. The most important thing for at least for what we're doing, you know, today and the next time is just knowing the values of sine and cosine for particular angles, and this is something that people learn in different ways. Some people like memorize values around the unit circle. This is what I'm talking about. I actually never learned it that way. I think more in terms of special shapes. But anyway, you should know special values of sine and cosine for particular angles. And I'm always going to use radians for the angles. But so the first ones which you need to know, first ones that I'm going to say at least, are ones that you can read off of the graph. They are these values here, where this is pi over 2, this is 3 pi over 2, 3 pi over 2. So these values would be sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is minus 1, and then sine of 2 pi is 0 again. All right, those are those 5 points that I put on the graph. You know, to me, the way I remember these is just by remembering what the graph looks like. So if you asked me, if you approached me on the street or in the club and asked me what is the sine of 3 pi over 2, I would actually, I don't really have that memorized per se, but I think about what the shape of the graph looks like, and then I'd be able to tell you within a few seconds. All right, and then similarly for cosine, the graph of cosine looks like this, where this is pi over 2, this is pi, this is 3 pi over 2, and then this is 2 pi over here. And so those values are, you know, similar, zeros and plus ones and minus ones. So for cosine, the cosine of 0 is 1, the cosine of pi over 2 is 0, the cosine of pi is minus 1, the cosine of 3 pi over 2 is 0, and the cosine of 2 pi is 1 again. So these are values for cosine that you can tell by looking at the graphs. Any questions about those? I hope these sound familiar to you. And then we have particular other angles which come from specially shaped triangles. So we have the 30, 60, 90 triangle, which of course is pi over 6, pi over 3, pi over 2, but nobody says that when they're talking about the triangle. But anyway, the picture you should have in mind is something like this. Has a 90-degree angle there. It has a 30-degree here, which is pi over 6, and a 60-degree here, which is pi over 3. And the sides of such a triangle must obey certain relationships, and it's because this triangle, the only way these angles can arise is if this is 1/2 of an equilateral triangle. And the easiest way to label the sides in that case would be 2 here, a 1 here, and a √3 here. So this picture you sort of have to memorize, at least if you think through in this way. This is the way that I think through the values of the sines and cosines of these angles. As long as you remember this picture, then you can say immediately what the sine and cosine of pi over 6 and pi over 3 are. So sine of pi over 6 Of course, you need to know sine is the opposite over the hypotenuse. So what would that be in this case? Yeah, 1/2. The opposite side, so I'm talking about pi over 6, which is this angle. The opposite side is 1, and then the hypotenuse side is 2. So this is 1/2. And then cosine pi over 6, being the adjacent over the hypotenuse, is root 3 over 2. And then we can also say, what are the values for pi over 3? Sine of pi over 3. Again, you do opposite over hypotenuse, but this time the opposite side is this one, because I'm looking opposite this angle, pi over 3. So it's root 3 over 2. And cosine pi over 3 is 1/2. All right. So these are how you do sines and cosines of 30 degrees and 60 degrees. Like I said, some people learn to just sort of memorize these values, and that's fine if you can do that. I don't really like memorizing things. Okay, and then finally, the other special angle arises from the 45-90, which of course is pi over 4 and pi over 2. So that is the right-angled isosceles triangle. And this one you can label the sides, the two sort of straight sides, I'll label them both as 1. And then that makes the hypotenuse be root 2 by the Pythagorean theorem. And so sine of pi over 4. So these angles, both of them actually, are pi over 4. So when I do the sine, I go opposite over hypotenuse will be 1 over the square root of 2. Some insane people insist on writing root 2 over 2. If you want to do that, that's fine. To me, that obscures where this comes from. If you write it as root 2 over 2, then it no longer makes sense as the opposite over the hypotenuse. But whatever. I'm always going to write 1 over root 2. And then cosine pi over 4 is also 1 over root 2, also known as root 2 over 2. All right. There's some kind of conspiracy among high school teachers to tell you that you're not allowed to have a square root in the denominator, which is, they gonna do what they do, I guess, in high school. But, oh, sure, yeah. I mean, this really, it is the same as root 2 over 2. If you multiply the fraction by root 2 over root 2, then on the bottom you get root 2 times root 2, which is 2, and on the top you get root 2. But there's no good reason to write it that way. I think this is like the insistence on writing it this way, I think, is a very old historical sort of computational thing, where if you wanted to actually write the decimal digits of this, you would look up in some book the digits of root 2, and then you could do long division and divide it by 2 if you really wanted to. Whereas this is kind of impossible to do using long division. Even if you know the digits of root 2, doing long division to divide 1 by that irrational number, it's not really, it's much harder than dividing a known number, dividing it by 2. That's easy to do. I think that's why people, in the deep past, people said you shouldn't write square roots in the denominator because it's very hard to compute the digits of such a number by hand if you had to. But nobody cares about that anymore. Either of those things you can easily type into a calculator if you really want the digits. All right. So these are all the special values of sines and cosines that I would expect you to remember. Anybody feel like I left anything out as far as those go? There are also angles which are bigger than 90 degrees, but those values can always be expressed in terms of these ones, and I hope you remember something about that, although we're not really going to come across those very often. All right. Okay, a few more sort of miscellaneous facts. Those were specific values of the sines and cosines that you should know. Miscellaneous facts. I would say, first of all, I only mentioned sine and cosine. That's because tangent is equal to sine x over cosine x. And so, to me at least, if someone ever asked me to find the tangent of something, I always just find the sine and the cosine and then divide them. Or you could say the tangent is the opposite over the adjacent. But anyway, tan can always be written in terms of sine and cosine, so it doesn't really, we don't really require sort of special discussion of tangent. Another random fact that we will use is this one. At least we might use. Sine squared x plus cosine squared x equals 1. Now, probably in high school or elsewhere, you learned lots of other random facts about maybe sine of 2x, there's a formula for that, or sine of a plus b, there's a formula for that. We're not going to use any of that stuff. Or if we do, I will just remind you. I'm not going to expect you to remember those formulas. All right? And then we have the three other trig functions, which you should at least know their definitions. There's the secant, the cosecant, and the cotangent. And the definitions of these, and this you just have to remember, there seems to be no rhyme or reason to these, but secant x is 1 over cosine, cosecant is 1 over sine, and cotangent is 1 over tan. So those, unfortunately, you should just memorize. There is, again, there is some kind of historical rhyme or reason to these names, although the way that we talk about trigonometry now has changed from, 200 years ago, and the emphasis now is different, and so these names don't seem to mean anything, or they don't seem to represent anything important anymore. Actually, in the old days, there were even more of them. There were like 24 of these or something, like every possible ratio of opposite over adjacent or adjacent over hypotenuse. They all had their own different names, which I only have heard about that stuff. Nobody cares about that anymore. All right. Okay, and finally, I'm going to say derivatives and integrals. What I expect you to know is just the derivatives of sine x is cosine x, and the derivative of cosine is minus sine of x. And this means automatically that the integral cosine x dx is sine x plus c, and the integral sine x dx is minus cosine x plus c. These can be a little tricky to keep straight, the signs, the plus sign and minus sign, but you got to keep it straight. All right, and I'm going to say also derivative and integral of the others, by which I mean, tangent, secant, cosecant, whatever. And I'm just going to say, look these up. I would not expect you to know those other ones, say, on a test. These ones, so basically everything that I just wrote, which I know is kind of a lot, I would expect you to be able to come up with this on a test or something. Any of these facts. I can't see that anymore. There's also a big batch of other formulas that I hope you have written down on a list somewhere or in the back cover of a textbook that if it comes up on the homework, I would expect you to go find the appropriate formula, but I wouldn't expect you to have them memorized. All right. Any questions about that? Or anyone feel like I left something out you're unsure of what I expect you to know or not? Of course, you can always ask me, before our next test or whatever if you're unsure. All right. Yes, sure. No, because the quiz on Friday is always just about what was on the homework, and so it's just logs. Yeah, logs and exponentials. But this is going to come up in what we're about to talk about, which is we're going to continue talking about the inverse trig functions. So we ready to proceed about that? All right. I will refresh our memory where we left off last time. We were talking about inverse trig functions. Remember, they are not exactly true inverses, but they're pretty close and still useful. The idea is, the reason you can't find a true inverse for something like sine of x is that it's not one-to-one. And the solution to this problem is we look only at a little chunk of it. We look only at a certain domain, and within the red box there, it is one-to-one. And so you can find the inverse just of that part. So we look at only this part of sine of x. which has this graph, where it goes over to pi over 2 here, back to minus pi over 2, up to 1, down to minus 1, right? You look just at a piece of sine of x, and then this can be inverted. The inverse just of that piece looks like, you take that same picture, but you interchange all of the x's and the y's. So the x scale now will go from minus 1 on the left to 1 on the right, and the y values will go from minus pi over 2 down here to pi over 2 up here. And the curve looks like the diagonal mirror image of the curve that you see up there. And so it has a vaguely same shape, but instead it goes that way. All right, and this is called the arc sine, or the inverse sine of x. All right, it looks like that. Its domain is the interval minus 1 to 1, and the range is the interval minus pi over 2 to pi over 2. This is called the inverse sine. I'm usually going to say inverse sine, but it's also called the arc sine. Those are synonyms if you ever see one or the other. Our book usually writes it with a little inverse. All right. So this is, it's sort of a picture of it, but if you want to be technical, the definition of this is, that when x is in the interval minus 1 to 1, this is the only time when you're allowed to do the inverse sine, but inverse sine of x equals y. This means that sine of y equals x. It's the inverse of the sine function. You can only do it when x is from the interval minus 1 to 1. And it also means where y is in this minus pi over 2 to pi over 2. That last bit that I just added is kind of important. That is this is sort of where I'm specifying or reminding you again that we only consider a chopped up version of the sine function. That y value, we always assume that it's in that interval from minus pi over 2 to pi over 2. All right. The way to think about this sort of in words, you could say inverse sine of x is an angle, I will say parenthetically, in this interval, minus pi over 2 to pi over 2, whose sine is x. This is how you want to think about the inverse sine function. An angle in minus pi over 2 to pi over 2, whose sine is x. So, for example, what is, let's say, inverse sine of 1/2? This is where, you will want to look at that big bunch of random facts that I told you about the trig functions at the beginning. I'm asking you, what is some angle whose sine is equal to 1/2? What do you say? Anyone remember? You can flip back in your paper. Pi over 6, yeah. So this is something that, you either just know this because you memorized all the values, or you might have to, like, I don't have this kind of thing at immediate recall in my mind. If you ask me what's the inverse sine of 1/2, I'll probably have to think for a few seconds, but I hope that you could come up with the answer eventually. So why is this true? This is true because the sine of pi over 6 is 1/2, right? This is the idea. Similarly, how about the inverse sine of 1 over root 2? What is the angle whose sine is 1 over root 2? The answer is pi over 4, etc., right? How about inverse sine? I shouldn't have said etc. yet. I'm going to do one more. Inverse sine of 0. What's the angle whose sine is 0? Okay, This is a good answer. Although, yeah, 0 is the answer I was looking for. This is because since sine of 0 equals 0, right? But he said, what about pi? Actually, also, can I say parenthetically, also sine of pi equals 0. That's true, but yeah, that's outside of the range. That's right. So we do not say, so also sine of pi equals 0, but we don't say sine inverse sine 0 equals pi, since pi is outside this interval that I keep on saying. All right. So if I say, what is the angle whose sine is 0? The answer is, actually, there's many angles whose sine is 0. There's 0, there's pi, there's 2 pi, 3 pi. But only one of those is the answer of the inverse sine of 0. And it's the one which is in this interval, minus pi over 2 to pi over 2. All right. Excellent. Okay, let's talk about some properties of the inverse sine function. So, basic properties. First of all, just because it is the inverse, at least of some little piece of this, the most important or most obvious basic property is this. What are you going to get when you do sine of inverse sine of x? X, yeah, that's the whole point of what an inverse is. That if you plug f inverse inside of f, or the other way around, you just get x again. So this equals x. And I'm just going to say when x is in minus 1 to 1, because that's a domain of inverse sine. And you actually are not allowed to plug any other numbers into the inverse sine function. You'll get, like if you try it on your calculator, it'll give you an error. And then this is also true. Inverse sine of sine x equals x when x is in minus pi over 2 to pi over 2. All right? Although this is kind of for different reasons. Like in the second one there, notice that x is being plugged into sine. And actually, you can plug whatever number you want into sine of x. It's just this formula will only work. This will only be true when x is in that interval from minus pi over 2 to pi over 2. So can I just set sort of as an aside? If x equals, say, 2 pi, then I do inverse sine of 2 pi. Well, if we actually compute this, sine of 2 pi is 0. So this would be inverse sine of 0, which is 0. That's not equal to, it didn't work that time, right? Because this is different from that. So this formula over here, that inverse sine of sine x equals x, that only works if x is in the appropriate range, or the appropriate interval. And this is why inverse sine is not really a true inverse. But it's pretty close. All right. Okay, here's something a little weird that we can do. We can evaluate stuff like, and you'll see, this will seem perhaps hopelessly weird, but you'll see actually this kind of thing is useful in a moment. What is the cosine of the inverse sine of x? This is a little weird, but turns out to be useful. You know, the sine of the inverse sine of x is x. What about the cosine of the inverse sine of x? This means the cosine of the angle whose sine is x, right? That's what that means. How could we find this? Actually, you can draw a picture. The angle whose sine is x, right? I can draw a triangle which makes the sine of some angle equal to x. Oops. Okay, I'm just going to draw some right triangle like this. And let's say this is the angle I'm talking about over here. and I want to make this angle have the sine equal to x. Of course, the sine is the opposite over the hypotenuse. If I want that to be x, I can put an x here and a 1 here. And now the sine of this angle will equal x, right? So the sine of this is, it's op over hype, which is x over 1, which is x. And that's what I'm trying to talk about, the angle whose sine is equal to x, right? So this angle, in fact, it is the inverse sine of x, right? Like that's what the angle is. It is the angle whose sine is equal to x. And what I'm asking is, can you find the cosine of that angle? The cosine of that angle would be the adjacent over the hypotenuse. Now, we don't know what the adjacent side is, but I think actually you could find the adjacent side because this is a right triangle, right? So what is, for now I'll write it as edge. What exactly is that? By the Pythagorean theorem, we would say x squared plus adjacent squared equals 1, and then we could solve for adjacent. What's it going to be here? Anyone want to add anything? Yeah, it's the square root of that. Great. That's what you get if you solve for the adjacent. So my triangle actually looks like x here, 1 here, and then this, 1 minus x squared down there. Because you're looking at this and solving for adjacent, but it's adjacent squared here. Yeah. All right, and so anyway, what's the cosine of that? Now you can see it is that weird square root thing over 1, the adjacent over the hypotenuse. So the cosine, in conclusion, cosine of inverse sine of x is square root 1 minus x squared over 1, which of course you don't need to write the over 1. It's that. Now this is not a fact that you should memorize, but I hope you believe me. We're actually going to use that fact in a moment. All of this work actually allows you to immediately say also what the tangent is. Anyone tell me what the tangent is? Maybe someone other than my two most popular volunteers. You're one of my two most popular volunteers. It's painful. Someone else? You want me to call on somebody? How about Ms. Gabriella? Yeah, you got to do the opposite over the adjacent. So that would be, this is the angle we're talking about over here. So you go opposite, which is x, over this one. Excellent. Thank you. Great. All right, strange facts about the inverse sine. You could also, if you wanted to, you could do like the cosecant of the inverse sine, whatever. All of these things you can figure out if you really want to. All right. Excellent. Let's talk about derivative of the inverse sine. It's not so hard to find the derivative of the inverse sine. Now, it would be cute if the derivative of inverse sine was inverse cosine, but it's not. It's actually something completely different from that. That would be fun, but it's not so. I want to talk about the derivative of the inverse sine of x. We're going to have a formula for this. The way to do this, we are going to do a similar trick that we've done a few times before. Whenever you want to find the derivative of an inverse, and inverse sine is kind of an inverse, the way to do it is by writing it again without using the inverse and doing the implicit derivative. So the strategy here is I start with y equals inverse sine of x, and then I want to rewrite using sine instead of inverse sine. So what that looks like is x equals sine of y, right? This is rewriting the other way around, because inverse sine of x is the inverse, at least for part of the function. And then here I'm going to do the implicit derivative. That involves taking the derivative on both sides, and then you just have to remember when you take the derivative of something with a y, you've got to multiply times dy dx. So what it looks like here, on the left side I get 1, and on the right side I get derivative of sine y is cosine y times dy dx. All right, this is the implicit derivative. And then you solve for dy dx. dy dx is 1 over cosine y. And we're almost done here, but really you want to write the answer in terms of x, right? Not in terms of y. And so you plug back in, somewhere around here we have a formula for y. It's at the very top. Y equals inverse sine of x. So really this is 1 over cosine of inverse sine of x. And there you go. Remember I said this looks weird, but it'll actually be useful for something. Here's the moment that we're all waiting for. Cosine of inverse sine of x. What is that? We just talked about it. If you go up a little. Cosine of inverse sine of x is here. 1 minus x squared. So, sorry, square root of 1 minus x squared. So that's what this is. 1 over square root of 1 minus x squared. And so this is our final answer about what's the derivative of the inverse sine. I'll write it again. It is this. And this also, I would say, falls in the category of don't memorize this formula, but when it comes up, you should be able to go find it in your notes. All right, 1 over square root 1 minus x squared. Any questions about that so far? This is the integral, the derivative of inverse sine. The integral of inverse sine is totally different, and actually I don't even know if I know what that is. It's not something that we're going to talk about soon. All right. Well, maybe I know it. I don't know. I certainly don't remember it. Okay, we got 15 minutes remaining. I think that's enough to talk about inverse cosine. It's very similar to all of this stuff that we've been talking about, although there are some important differences. So let's try to do all the same stuff for inverse cosine of x, all right? We must begin by looking at the graph and first of all deciding which piece should we take to invert, all right? Now for sine of x, we took the piece from minus pi over 2 to pi over 2. Remember what the graph of cosine looks like. It looks like this. Now we need to choose a piece of this where it's 1 to 1. If we try to choose the same old piece, don't write this down because this is going to be wrong. With sine, we chose this, right? Oh, what's wrong with that? I said this is going to be wrong. Why can we not use that chunk here? Yeah. Yeah, it's not 1 to 1 there. The whole point of choosing a piece of the function is you need to choose a piece where the function is 1 to 1. That's not going to do it. Anyone want to suggest an alternative sort of little box to draw where it really is 1 to 1? Of course. Yeah. 0, yeah, how about from like here to here? Is that what you meant? Yeah. Yes. Yeah, so this is actually pi on the picture. And this is 0. This is the piece that we're going to invert. Now, this is not the only way you could have done it, although this, to me at least, seems the most natural way to do it. Although, of course, you could have, say, chosen that box over there to the left. You could, or you could even choose this box over here for some reason. But the first one there, the one that she said, is the most natural one to use. So, let me just redraw this and just zoom in on that part. Only here, like that, right? And of course, the y values are minus 1 and 1. So this is cosine x. The domain that I'm considering is only 0 to pi. And the range is minus 1 to 1, right? And so this is the part which we're going to invert. And it actually looks pretty different from inverse sine, or the curve vaguely has the same shape, but, sorry. When I invert this picture, what it looks like, so the original picture has only positive values for x, so when I invert it, it will have only positive values for y, right? And now that the 1 and minus 1 are now going to be on the x-axis, and the 0 and pi are now on the y-axis. And I'm going to try to draw this curve, but reflect it around the diagonal line, and I hope I do this right. The curve begins at, say, over here, this value, x equals 0, y equals 1, should go down to x equals 1, y equals 0. So the curve sort of starts here and goes up to there, like that. This is the graph of inverse cosine of x. And this point where it goes through here, that's pi over 2, where it goes through the y-axis. All right, and let me just say, inverse cosine of x has domain -1 to 1, and range 0 to pi. So it is kind of different from inverse sine of x. I mean, obviously it's not exactly the same, but even like the range of it looks different. All right. Any questions about the setup here? This is how you have to do inverse cosine in this way. The answer of inverse cosine is always positive. It's not going to be negative. We got 10 minutes, 12 minutes. How about I want you guys to try. You try to find sine of inverse cosine of x and tan of inverse cosine of x. You should be able to do this in the same way that we just did something like cosine of inverse sine of x. You make a triangle. Try and set up a triangle. Label some sides with x's and whatever. See if you can copy what we did before. Yes, yeah, because we want the cosine to be x, so you might as well make the adjacent side x and the hypotenuse 1. Yeah. I mean, you could do it in other ways, but there's no reason to. I'm going to come see how you're doing. what you had inside the parentheses there. Yeah. Yep. All right, it looks like people did pretty good with them. So this is the setup, right? The inverse cosine of x is the angle whose cosine is x, and so the triangle that you make should be set up in this way so that the adjacents over the hypotenuse will be x over 1, which is x, all right? And then you find the other side using the Pythagorean theorem. It should end up being this, which looks familiar, square root 1 minus x squared. And then you take the sine of that and the tangent of that. So the sine would be opposite over hypotenuse. Opposite is here now, and the hypotenuse is 1. So it's going to be sine of inverse cosine of x shall be just that square root, 1 minus x squared over 1, right? And then the tan of inverse cosine x is the opposite over the adjacent. So it'll be that guy divided by x. Opposite over adjacent would, on this picture, would look like this is the opposite, this is the adjacent. All right? It looked like everybody was getting those. I hope so. Any questions about that? I hope you're doing okay, the folks back home. Yeah, the tan is the opposite over the adjacent, all right? And since the angle is over here, this is the op, and this is the adjacent. All right, the op is this side, root 1 minus x squared, and the adjacent is this side, which is x. All right. All right, we still got a few minutes left. Can we talk about the derivative? How about this? Can I have you guys try to do the same thing we just did for the sine, but using the taking the derivative? So I hope you remember what I did to do the derivative of inverse sine. You write it first of all as y equals inverse cosine x. Turn this into something using cosine, not the inverse cosine, and then do the implicit derivative. So rewrite using cosine, then do the implicit derivative. All right? You should be able to follow sort of step by step what we did for the inverse sine, and everything will work out, you know, similarly but slightly different. See what you think. Any questions from the folks at home? Nope. Who knows if they're even there? All right, looks like people are doing great with these. I'll just do my own version real quick. So when you do the, you rewrite things, right? Y equals inverse cosine x is the same as cosine y equals x. You take the implicit derivative on both sides. You get minus sine y dy dx equals 1 on the right, and then you divide the that minus sine y. And then this just replacing or plugging back in for the y, because I want my answer in terms of x. Dy dx equals 1 over minus sine of inverse cosine x. And then this sine of inverse cosine x is something we just figured out a few moments ago. And if you look up here, it's this, right? Sine of inverse cosine of x. And so I can plug that in. My final answer. Oh, sorry. I did something that I always hate when people do. I shouldn't put an equal sign right there. These are two separate equations. I'm not into that. Okay, anyway, the formula is derivative of inverse cosine x is 1 over minus square root 1 minus x squared. This is the formula. The derivative of the inverse cosine. What? Well, I'm kind of done, but I don't know what happened. I just got, yeah. I think I disconnected from the Wi-Fi. Well, I guess it's time to stop. Yeah, that was the last thing I was going to say anyway, so I don't know what happened. Next time we'll talk about inverse tangent. It's going to be great. Yes. That's right. Yep.